Chapter 7, Part 4, Mechanisms of Elimination, E2 mechanism. Okay, let's take a look at the mechanism and how this actually works, and then we can talk about predicting the products. So our first mechanism is a very generalized mechanism. This is beta elimination, also known as 1-2 elimination. So let's first talk about what we mean by beta. So carbons are typically labeled as alpha, beta, gamma, delta, epsilon, going through the Greek alphabet, depending on their proximity to the functional group. So in this case, our functional group is the alkyl halide, and so the carbon that has the halogen attached to it is the alpha carbon. The carbon that is next to the alpha carbon is the beta carbon, and so forth. So the hydrogen that is on the beta carbon is called the beta hydrogen, and the leaving group is on the alpha carbon. When a base is added to this, the base can actually pick up, let me use a different color. The base can actually pick up the hydrogen atom. These electrons can form the double bond, and we can take these electrons and kick out our halogen with it, forming an extra lone pair here. We also end up with the conjugate acid of the base that was used, and an ion of our leaving group. So there are two possible mechanisms for this. There's the mechanism that I already demonstrated. We're going to look at that again. And that one is very parallel to SN2 reactions. So recall that an SN2 reaction is a bimolecular nucleophilic substitution. The mechanism happens all in one step. A strong nucleophile is necessary. In an SN1 reaction, it's a unimolecular nucleophilic substitution. There are two steps in the mechanism and a carbocation intermediate, and essentially any nucleophile will work. First, we're going to discuss the E2 reaction mechanism. This one is very similar to SN2. So your typical substrate is going to be an alkyl halide, probably with various substitutions, probably secondary or tertiary, but not limited to secondary and tertiary. And the key thing is that you have to have a hydrogen in the beta position. And you have to have a base that is strong enough to pull off that hydrogen. And then through the E2 mechanism, you'll form an alkene, the conjugate acid of the base, and you'll have your leaving group as an ion. A quick reminder, this is what that mechanism looks like. The base pulls off the proton. The electrons between the proton and the carbon go down to form your new alkene. And then the leaving group is kicked out. So, for example, let's say we have isopropyl bromide, or you call it 2-bromobutane if you're using IUPAC nomenclature, and ethoxide. Ethoxide is a really common base used in E2 reaction mechanisms. It is a pretty strong base. It's also a good nucleophile, so you might see a little bit of SN2 substitution in this setup, but the ethoxide can pull off one of the beta hydrogens, create a pi bond between the alpha and beta carbons, and then kick out bromide. And what this will give you is a new alkene plus ethanol plus bromide. And the rate of this reaction shows that this is a bimolecular reaction because the rate is equal to the rate constant times the concentration of isopropyl bromide times the concentration of ethoxide. So there is a potential problem here where you have two different beta hydrogens. On our different beta carbons, first we have 2 beta hydrogens here, but then we also have 2 identical methyl groups that are also beta carbons to our alpha carbon that has the halogen on it. And between those 2 methyl groups, there are 6 identical beta protons that could be used to eliminate the bromine and form an alkene. So which one do we use, and how do those products differ? So in our first example, if we were to use the gold-colored hydrogen to eliminate the bromine, we would end up, let's use orange ink to demonstrate this. We would create a double bond here and kick out the bromine. That would give us this alkene as our product. If we use the silver hydrogen, we're still going to use these electrons to create a double bond. We're still going to kick out the bromine, but we end up with this alkene, or you could also draw this alkene, depending on which methyl group you used, or they're really the same because there's rotation around this double bond, or this single bond, but I wanted to draw both of them for you anyway. But the question is, how do we know which of these we're going to do? Are they both formed equally? And the answer is actually that it depends on the identity of the base. So this brings us to Zaitsev's rule. Now, Zaitsev's rule is actually where all that stuff about alkene stability came from as well. So in summary, Zaitsev's rule says that if you are using a small base, such as hydroxide, ethoxide, you're going to form the more substituted, more stable alkene. If you have a bulky base, think tert butoxide or phenoxide, isopropoxide, you're going to form the less substituted, less stable alkene. So let's talk about why. Keeping in mind that Zaitsev's rule says that the more substituted alkene is more stable, we should automatically assume that if possible, we will form the more substituted alkene. So let's take a look at the example we were looking at a second ago. This is the same molecule from our previous example with the silver and gold hydrogens. It's just last time it was drawn out like this, and now it's drawn out in 3D. If we have a small base around, ethoxide is going to want to pull off the proton from the more substituted carbon so that it can form the more substituted alkene between the 2 carbons and kick out the bromine. But before we draw our product, let's think about what this transition state would look like. When the ethoxide is trying to extract that proton, this bond between the hydrogen and the carbon is going to begin to break as the bond between the 2 carbons, the double bond, begins to form. So this gives us kind of a complex transition state where we are forming this bond, breaking this bond, and forming this bond. Keeping in mind that the more substituted alkene is more stable, the transition state that features the more substituted almost alkene is also going to be more stable. And the more stable this is, the better off we're going to be with this developing negative charge on the bromine as well. There are a lot of things going on here. And this will lead to the more substituted alkene. So the more stable transition state is more likely to occur. And this is an example of kinetic control. This reaction is dependent on the stability and free energy of activation. I also want to point out that it says 69% here. This is the yield of the reaction. So if you put in an expected amount of your compound and your ethoxide, you can calculate a theoretical 100% yield of your product. But most organic reactions do not go to 100%. You may end up with some of that less substituted alkene. You may end up with some substitution products. But in this case, you're going to get only 69% of your expected product here. And that makes this the major product, because whatever else you're forming cannot come out to more than 31% of the total. So 69% is much greater than 31%, and therefore we call this the major product. Now, Zaitsev's rule tells us that if we have a bulky base, the less substituted alkene will form. So, for example, potassium T-butoxide is a common example used for a bulky base. Look at how huge all these methyl groups here are going to be, right? That's going to be a huge electron cloud. Just like when we were talking about nucleophiles and we said that if you have steric hindrance at the carbon containing the leaving group, a nucleophile can't get in there. A bulky nucleophile also cannot do a backside attack. Same thing for a bulky base. A bulky base is not going to be able to access this proton as easily as it can access one of these 6 protons that are out here on the periphery. So it's going to access the less substituted protons. And you will get that yield in 72.5%.